I need to share my slide. Can you guys see my slides now?
Yes.
Okay. Let's start. So good afternoon, everyone. I'm Peiheng, an operations research analyst working at Norfolk Southern, specializing in network modeling and optimization. Thank you. My work is mainly about the railroad blocking plan and the train service design. Thank you so much for inviting me to give a talk on coding in Python. So actually reminds me the days back to school. So I was involved with Institute of Transportation Engineers and served as the president of the student chapter. And we have similar events like you guys do here every semester. So from the announcement earlier, I think you guys all know today I'm going to talk about how to speed up the shortest path algorithm implementations by using proper data structures in Python. So today's talk is not a comprehensive overview on data structures in Python. We only cover those we will use for the shortest path implementations. And for the stat and dictionaries in Python won't be covered today. Okay. And I hope today's presentation will be as more interactive as possible. And you guys can stop me anywhere, anytime, if you have any questions. Okay. So before we started, I need to put a disclaimer here because I'm still using the template from the Norfolk Southern. So to be clear, this presentation is solely the personal work of myself, and it's basically the general information regarding the shortest path algorithm and the underlying data structures. So it is for educational purpose. And opinions of today's presentation and expressed in the following slides are those of myself and not those of Norfolk Southern. Okay. So this is the guideline of today's presentation. So it has 6 parts. So in the first part, I will go over some general background information in shortest path algorithm and shortest path algorithms. And then we will dive into the 3 special implementations of the modified label cracking algorithm, which is one of the shortest path algorithm, and talk about the implementations and how to build the implementations using different data structures. And then we will look over some of the potential improvement over the examples we covered in session 2, 3, and 4. And we will conclude our presentation today in section 6. Okay. So a quick question for you guys. So how many of you have implemented shortest path algorithms on your own? Anyone? Okay. So even you haven't implemented shortest path algorithm, but the shortest path problem is quite common, and we face it almost every day. So one possible case is that I would like to visit your campus after pandemic someday, and I decide to drive there, but I don't know how to get there. So I will properly ask the Google Map or Google Navigation to give me a path to indicate me how to get there. And I want to know how long it will take for me to drive there, right? And the app itself will probably call we'll call the shortest path algorithm, and it will probably be the A-star shortest path algorithm, which is different with what we discussed today. So, and the shortest path algorithm is one of the most fundamental algorithm in network modeling and optimization. And we have two main categories on shortest path algorithm in terms of how we deal with the distance label. So the first category is label setting algorithm, and among many of them, Dijkstra is the famous one, I guess. You may have heard or used it. Okay. And the other category is called label cracking algorithm, and it has many variants. And today we are going to focus on one of them, which is the modified label cracking algorithm. Okay. So no matter which shortest path algorithm are you using or you're going to implement, so you need we need a general or genetic notation system. So basically, we denote our network, the direct network, as G, with a set of nodes and a set of links. And for each link, we will have the cost associated with it, represented as Cij. And for each node, we will have a set of outgoing links. And the outcome from any shortest path algorithm is basically the distance label. Tell me the distance from one point to the other point. And the other is the predecessor. So let's use the 6-node network as an example. So for those of you which are not familiar with the shortest path algorithm. So here we have 6 nodes on the network, and we have those the number along each link or arc that represent the cost or distance or any metric you would have for this link. And for each blue rectangle, we have 2 numbers here. The first one is the distance from the source node, and the second one is the predecessor. So let's use one simple example. So in this one, someone already calculated the shortest path for us and update all the predecessors and distance labels. So for node 3, okay, the source node here is 1. Okay, so for node 3, I know the distance from the source node to this one is 4, as indicated by the first number. And the predecessor, or the node before node 3 is 1. So basically, I can have the shortest path from 1 to 3 in terms of the node sequence is node 1 and node 3, and the distance is 4. Okay, and another more complicated example would be 6. Okay, so if we look at the 6, we know the distance from the source node, which is 1, and the distance would be 9 from 1 to 6. And the and the predecessor of node 6 is 5, and the node prior to 5 is 3, and for 3 the predecessor is 1. So now we have the complete path now. So the shortest path from 1 to 6 in terms of the node sequence is 1, 3, 5, and 6, and the distance is none. Okay, any questions here? It would be great. It would be great if someone can turn on the video. Otherwise, I feel like I'm talking to myself. Okay. Oh, okay. With the those notations, we can first present the modified label crafting algorithm. Okay. So for you to better understand it, I cut the this pseudocode into 5 different sections. Okay. So the first part, we will go over those sections one by one. So the first part is the initialization on distance labels and the predecessors. And the second one is the termination check or your stopping criteria. So one major components I didn't mention is this list here, the list here, or we usually call it as the scan eligible list. Basically, it's a set of nodes which might violate the optimality conditions in shortest path problem, which is here, this one. Okay, as long as we have any nodes in this lead, we will continue our shortest path algorithm. So each time we remove one element or one node from this list, and then for each outgoing link from this node, we are going to check the optimality condition here. This triangle, the triangle inequality function here. So you can simply interpret it as that, do we have a shorter path from I? Do we have a shorter path from I to J? Okay. If we have a shorter path here, we are going to update our distance label and the predecessors. And then the final step is that we are going to check whether this node J has been this scan eligible list or not. If not, we simply put it there. Okay. Any questions here on the pseudocode? Okay, good. Okay. Okay, let's look at again from a different perspective on the pseudocode. So, so for the first part, which is the initialization on the distance label and the predecessors. So basically, we set up the values with the initial values. So they are constant operations, and so as the termination checks, and for the label correcting, basically we enumerate, we loop through every outgoing links and check the optimality conditions, and set up, update the distance label and predecessors accordingly. So those are constant operations as well. So by constant operations or the operations in constant time, so basically we already reached the best we can do. So there's not much you can do about it. But we have 2 other parts on the scan eligible list updating. The first one is the removal part. The second one is the adding part or the inserting. So they are subject to implementations. So in other words, the performance is up to our own implementations, and they are the key to efficient implementations. So in the following sections, I will focus on these two critical operations on the list updating. Okay. So because as you can see that from the pseudocode, the algorithm doesn't specify how to maintain and update the list. So we will have some possible updating strategy here. So you can simply remove a node from the front, from the end, and from anything anywhere in between, and you can add it to the front, to the end, and to a random position. Okay. So in fact, how to maintain and update this scan eligible list leads to different implementations of the modified label crafting algorithm. So among many of them, we have three very known, very efficient implementations, special implementations, which are the FIFO implementation, the DAC implementation, and the best search, the best first in implementation, or it is essentially the distrust algorithm. But notice that we actually don't have a official name for the last implementation, and we will come back on this naming later when we reach there. Okay. So the FIFO implementation basically maintains the scan eligible list as a first in, first out queue. As you can see that from the pseudocode, basically we remove the first node or the node at the first beginning from the scan eligible list and put it to the end. And because its time bound is the big O MN, so it is also known as the big O MN implementation as well. It is a very straightforward and simple algorithm. Because the FIFO implementation requires that the node to be removed from the beginning and to be added to the end, right? So we need a data, sorry. We need a data container which supports either sequential access or random access for us to implement it. And the built-in list in Python actually is a good choice for us to implement it. So we will first start our implementation using the built-in list and work on the improvement using some other data structure later. So at least my implementation in Python and pseudocode side by side for a clear comparison. And we all have those on those two. I cut them into these 5 sections so we can do a side by side comparison. Okay, so the first part is the initialization. We initialize the distance label and the predecessor. Note that the part of the initialization on the distance label and the predecessors are not included in this function. So the caller of this function is responsible for part of their initializations. You can find the details in my GitHub page. Okay. And the second part is on the termination check whether this set is empty or not. And then we have the label correcting. So basically, we get the node and loops through each outgoing link from this node and check the optimality condition. And if we find a shorter path, we will update the distance label and predecessors accordingly. And finally is the list updating. So if the J or the tailing point of the link is not in the scan eligible list, we will simply put it to the end of this queue. Okay. I will pause here for a short time for you guys to go through the Python implementation.
Excuse me, I've got a question about the
Sure.
what is get node I here? P node equal get node I. I didn't get the difference yet. The line below it, yes.
Get node. Basically, the I here is the node index. I want to get the node object to reach its attributes. For example, the outgoing links. The I is the index, just the index, and I get the corresponding node object. I'm using the OOP, object-oriented programming. So I wrap up the node as a class, and I store the node ID, the outgoing links into it. So then here I need to get a corresponding object for me to reach the outgoing links from it. Okay.
All right, I got it. Thank you.
Okay, clear? Any other questions? Okay, we can move on. Okay, so this is a very simple and intuitive implementation, as you can see from the previous slides, and you probably will be happy with the implementation because the even with the list we have a pretty good time bound, so which is polynomial. So let's go over those the time analysis, time complexity analysis again here. So for this pop zero, okay, I think I missed something here. So sometimes the name of Python building list is kind of confusing because the building list is not a classic list we were talking about as the single linked list or double linked list. So if you check the implementation of the building list is actually is array. It is array based implementation. It is very similar to the vector in C++. So the list is very good at appending. So basically you put everything to the end, but not any operations near the front. For example, the pop zero here. So it will take the linear time for the Python list to do these operations. And here that for this, if J not in the list check, the presence check, it involves a linear search. Basically, we will retrieve all the elements in this list to see if the J is in there or not. So it takes linear time. Okay. So those two linear checks, you may don't think that because they are linear, so they are actually good, and you probably satisfied with the implementation because it is simple and it's polynomial time bounded. But if you run the this algorithm or the implementation on a large scale network, you those two linear time operations might become computation bottlenecks. So I did a small numerical test here. So I run my my algorithms on the Chicago network, and this operation, which is basically the presence check, is executed around 1.7 million times. So this is quite a lot. If we could do something on these operations, the benefit on the overall running time could be significant. Okay. So the question is that how can we do better on these two linear time operations? First, we will skip the pop zero operations because we're going to encounter this again in the next special implementations, and we just focus on this linear time presence check. So for network applications, we have a very simple observation. So for the scan eligible list, which holds the nodes that may violate the optimality conditions, its size cannot exceed the size of the nodes on the network. So in other words, it cannot hold more nodes than what we have on the network, right? It's very simple and straightforward observation. So with this simple observation, we can simply introduce a indicator array at the size of n. So basically, it is a fixed length. And we denote the status as 1 if the corresponding node is in the list. Otherwise, we denote it as 0. So basically, with this status array, the presence check now will take constant time. Okay. Any question here? Okay, good. So we re-implement the FIFO implementation using this constant time check with 2 more operations. The first one is the initialization. Basically, we need to set up this status array at the first beginning. Okay, and here we use the list generator to achieve the maximum efficiency. Basically, we're running this part at the speed of C. And then later on, we need to, after we put a source node to this list, we need to set up the corresponding status as 1, basically to indicate that the source node is already in this scan eligible list. And each time, if we remove a node from it, we will reset its status to 0. And then later on, in the later updating, if the node is not in the scan eligible list, we will put the node into the list and update the status to 1. Okay. And all the others are remain the same. Okay. So let me know if you guys have difficulty in understanding those source code. Okay. So now you may wonder what would the running time be for these 2 implementations. One is with the linear time check, the other is with the constant time check. So I conduct a numerical test on the middle size network, which is the Chicago Sketch network. It has 933 nodes and 29 and 50 links. So it is middle size. And we run the 2 implementations repeatedly over all those 933 nodes to get all pure shortest paths on this network. Basically, the shortest path between any 2 nodes. Okay. And we run 5 times for each implementation and calculate the average, excluding the highest and the lowest. And this is the statistics from these 2 implementations. So with these the linear time operations, the running time is 4.9 seconds, and with the indicator array, which is the fixed time, which is the constant time, so the running time is reduced to 3.153. So the reduction is about 36%. It's very significant. And at least the running times from the equivalent C++ implementation as well here, just as the benchmarks. Okay. So one more thing I want to emphasize here is that because for each implementation, for the first time run, it involves compiling the code from source node to the bed node. So actually, you need one addition run in addition to besides those five runs to have the fair comparison. Okay. Okay, so as we can see that the FIFO implementation is very straightforward and easy to implement, and its time bound is polynomial, but actually it is rarely used in research or practice because it is considered slow. So in this session, we're going to cover another special implementation of the modified label cracking algorithm, which is one of the shortest path algorithm on a sparse network. So this implementation is known as the DAC implementation. So basically, we maintain the scan eligible list as a double-ended queue, or DAC, or DEQ. So, and we always remove the element from the front and add the node to either the front or the end based on the heuristic here. Okay. So here, so let's go to the pseudocode here. So on the remove part, it is exactly the same as the FIFO implementation, but on the adding part is different. So basically, after we found this node is not in the current scan eligible list, we're going to do a further check. We need to check whether it was in this scan eligible list or not. So if yes, we put it to the front. If no, we put it to the end. So this is a very simple position-based heuristic for this DAC implementation. Okay. In order for us to implement, we still need a data container, which either supports sequential access or the random access. And we will start the implementation in the next slides using Python, using the Python built-in list. And as we can see from the pseudocode, we need the node status in history to indicate whether a node was in the scan edible list before or not. So we could introduce another data container to store whichever nodes were there. But from the example in the FIFO implementation, we know that it will trigger another linear time search. So it could be a bottleneck if we run our implementation on a larger scale network. So we borrow the same idea or the similar idea from the FIFO implementation. We introduced the new status array with one additional status 2 to indicate the node is not in the current scan eligible list, but it was there before. Okay. Any questions here? Okay, good. So at least my my Python implementation along with this pseudocode side by side for a better comparison. So as you can see that, so each time we we remove a node from the beginning, we need to set its status to 2, basically to indicate that the node was here before, but is no longer in it. And on the adding part, we do the check. So to check whether it is in there or was not in there before, and update the status to 1. Basically saying that the node is now in this scan eligible list. And all the other powers are exactly the same. Do you guys need more time to go through the node here, the code here?
Sorry, I didn't understand what the insert does here.
Uh,
Insert. What insert does to the set? Yeah.
Clear?
Yes.
You don't understand why we need these operations?
Somehow, yes. Actually, you insert when the node J is not in the set, but it was in the set earlier.
Yeah, that is actually a very good questions on the heuristic itself. So basically, this one is a single source shortest path algorithm. So basically, we find the shortest path from one single source to all the other nodes. So you construct the shortest path tree, right? It's like a tree. And if you update the distance label, anything on the tree, and anything after going from this node will be properly be impact, right? So
Yeah.
that's the whole logic. So if you update something, so basically means that the node was there before. So if I update it, I will put priority on this node because I know I will have some ripple effect propagation back to the very end. So I will just put it at the first beginning because we always remove the node from the front. Okay, and if not, I simply put it in to give it a lower priority. So that's a very good question on the heuristic itself. Okay, so you guys now are all clear on this one?
It makes more sense now, but not completely.
Okay, it's very intuitive. Okay. So we still have some the issues with this simple implementation. So as you can see that, or from the previous discussion for the 5.0 implementation, the pop zero takes linear time. And because of the underlying implementation of the Python built-in list is array, so the insertion itself will take linear time too. So both of them are linear now, okay? So do we have any solutions on these two linear time operations? So because this implementation is called the DAC implementation, and we have a DAC probably in every programming language. So why not use the DAC, the data structure, which is dedicated to facilitate those operands. So actually, in the next slide, we are going to do a re-implementation and replace the pop zero and insertion with their equivalent from the DAC, and both of them will take constant time. So I list the base implementation using the Python built-in list and the advanced or the re-implementation using the DAC from the standard library side by side. So I will go through this one by one. So the DAC itself is from the library collections, and we simply construct a DAC or the scan eligible list here using its default constructor. And then we put this the source node to it, same as the list. So we use append. And instead of using pop zero here, we're using pop left. And on the insertion side, we use append left. Okay. Do you guys have any questions on the re-implementation using DAC? Okay, I guess we can move on to the next slide. So I run the same numerical task using the same network and the same testing strategy. And as you can see that with the Python built-in list, the average time is 2.5, and the re-implementation using the built-in DAC is 2.433. So the reduction is only about 4%. It's not that significant as we saw in the FIFO implementation using that constant time check. And we even observe a slower implementation if we use the DEQ, the DAC, over the vector for the C++ equivalent implementations without the compiler optimization. So here is the questions for you guys. Why will this happen? So you can keep this question in mind and think about it after this workshop. It will help you understand the underlying reason, in terms of the memory allocations behind the Python case here. So so for the FIFO and the DAC implementations, both of them using the position-based heuristic, right? We move the element from the beginning and add the node to either the front or the end, okay? So another intuitive heuristic will be that remove the node with the minimum distance label and add a new node to where it is needed. So this one is essentially the Dijkstra's algorithm as indicated here in this pseudocode. So as I mentioned before, it doesn't have an official name. So you can call it as best first search or minimum distance label implementation or simply the Dijkstra algorithm. The naming here doesn't matter as long as you know that this implementation adopts the best first search rule. The best first basic here is that we remove the node with the minimum distance label. Okay. Do you guys have any question here? Okay. So you can start the implementation with any data container as long as you have a way to find the node with the distance label, okay? So we can start the implementation using the built-in list as a base. And basically means that we need a linear search to find the minimum distance label from a set of node, okay, which are least the implementation here. So it's very straightforward. Basically, we loop through all the nodes to find the one with the minimum distance label, okay. So here is the Python implementation with this hyper function. Is on the left side, and on the right side is the pseudocode itself. So we can do a side-by-side comparison now here. So the initialization part is exactly the same, and on the removal part, there's a caveat here. Because in the pseudocode, it seems that we have only one option here. We basically remove the one with the minimum distance label. But actually in the true implementation here with the hyper function, we have two steps. The first one is for you to find that node. And the second one is that you need to remove this node from the scan eligible list. Okay. And then we set the status to 0. Okay. And on the second updating part, there's no such thing. Okay. We simply put it to the end and update the status to 1 to indicate the node is here. So this implementation is equivalent as the raw implementation of that diagram algorithm. So basically, you will have two set of nodes. One is the with the permanent label. The other is with the temporary distance label. So this one is equivalent implementation. So that's the reason it is essentially the diagram algorithm here. Um, so, so because for that implementation, we still need to maintain a helper function to help us find the node with the minimum distance label. So why not we use heap? Because the heap has a underlying has the underlying sorting features. Basically, we can combine the data container and the helper function into one. So this is pretty nice. And the most importantly is that if we use the heap in our implementation, it will bring down some of the key operations from linear time to either constant time or logarithmic time. So here in the pseudocode, let's do some of the analysis here. So for if we use the binary heap, so for us to find the element with the minimum key. So basically, it is a constant time operations for the binary heap. And for us to delete it, the minimum one, or we put a new one into it by insertion, or we decrease it if we found a lower key. So all those three will take a logarithmic time for binary heap. Any question? So we're going to re-implement our algorithm using this binary heap. And Python has a binary heap called heapq from the standard library. So we can simply import it and use it here. So, and we first need to create a heap using the heap file to convert the list to a heap, and then we will insert the first or the source node and its corresponding distance labels into it. Okay, and then later on, because the heap queue basically combine the operations find min and delete min together, so we will only have one operations here. It is called heap pop. That will pop the node with the minimum distance label and remove it from this heap. And then later on, we will put the node into this heap after the label correcting. But I guess you guys may already notice that my implementation is a little bit different with the pseudocode itself. So the question is here is that, do we miss something here? If you do a detailed comparison on its two sides. So right, we don't have the check on the distance label. So whether it has been updated before or not. So if the distance label is infinity, basically means that it has never been updated before. if the label, the value itself is less infinity, basically it means that we already update in the previous label correcting. So why do we miss this operation or this comparison? The reason is that the heap queue doesn't have the decrease key operations. So basically, you have a new value on this key, and you want to reduce the key from its previous value to this new value, and it doesn't have this operation. So now the question is that, is this implementation still correct? So if no, why? If yes, what will be the side effect if we miss this check? And how can we resolve this side effect? Okay, you can keep that in mind. And let's look at the CPU time comparisons here. I need to move my status bar so I can see the value. Okay. So as you can see that the raw implementation without a heap, the CPU time is 3.75 seconds, and the heap digestion algorithm or the digestion algorithm implement in heap takes only 2.337 seconds. So the reduction on the running time is about 30%, 38%. So which is quite huge. Okay. Okay, because for those two implementation, the base and this the heap implementation, we all adopt the best first search rule. So with that, so can we still consider this implementation as one of the label correcting algorithm? Or in other ways, that is this implementation capable of handling networks with negative circles? So those are very two important questions if you're dealing with network having negative circles. Okay. Um, okay. So basically, we're done with the three special implementation of the modified label correcting algorithm. And we already seen that those simple strategy or techniques for us to put the shortest path, the performance in terms of the running time. So a natural question will be that, can we do better, or can we do any further improvement over them? The answer is yes. So let's first take a look at the heap implementation, which we just covered before. So in our previous implementation, we use the heap queue from the Python standard library. As I mentioned before, it is a binary heap. So that binary, it basically the underlying data structure is a tree, it's a binary tree. So that's the reason we will have some the logarithmic time-bounded operations. So, and there's another heap which is more advanced called Fibonacci heap. It offers better performance on the decreasing k these operations. So basically, we can reduce the time bound from logarithmic to constant time just for this particular operation. So if we can re-implement it using this advanced heap, we can further bring the time bound from big O m log n to big O m plus n times log n. And this is actually the best time bound we can achieve for the heap implementations. Okay. But the problem here is that the Python standard library doesn't have built-in Fibonacci heap. And if you want to implement it from scratch, it is more complicated than implementing the shortest path algorithm here. So do you guys still want to give it a try? Okay. Another one is for the DAC implementation. And so the DAC from the collections library is by design to be efficient, but it still has dynamic memory allocations when size expands. So, and those dynamic memory allocations will trigger some extra cost, and those costs will be added to our overall running time. So we want to avoid them. So how can we avoid those extra costs? So we use the simple observations from before. Basically, the scan eligible list cannot exceed the number of nodes we have on the network. Okay. And we can simply introduce a simple DQ using this array as size of n, and we implement it in C and with the Python C API and convert it to an extension page. So basically, we do the same thing as the standard library DAC does, and run the numerical test with this simple DAC C. So you can see that we reduce the time from 2.433 to 2.34, so which is another 4% improvement. Okay. And you can also go to my GitHub page to check the implementation details. I have two implementations. One is implement in Python for this simple DAC. So for demonstration, it's easy to understand. The other is implement in C using this C API. So it's for the high performance. You can check both of them to get the insight. And actually, this DAC implementation with this simple DAC is still not the best one. If you want to find the best DAC implementation, you can go to my GitHub change and check a project called Path for GMNS that has the best DAC implementation in C++, but it is easy to understand. Okay, so let's give an overview on what we have done. So basically, we use an indicator array rather than the built-in X in S operations to check whether an element is in a data container or not. So basically, we reduce the time from linear time to constant time, and we adopt the built-in DAC to replace the built-in list and the corresponding pop zero and insertion operations, and bring those two linear time operations to constant time equivalent through pop left and append left. Okay, and we replace the built-in and DAC with a simplified array-based DAC for the DQ implementation to avoid any extra cost on the memory allocations. And we introduced the binary heap, which is the heap queue from the standard library for this best first implementation or digester. And here is the list of all the numerical tests and the running times. Okay. As you can see that the DAC implementation and the digester algorithm usually has better performance than the 5.0 implementation. Okay. Okay. So here is some good references on coding, so if you want to learn more, so those are very good references. And because Python has a close relationship with C and C++, we already, which we briefly touched in my previous examples. So learning something from C and C++ will help you to better understand the Python and help your coding skill in Python too. And I list several references from C++, and you can check them later. Okay. With that, I guess I will conclude my presentation today, and I would like to answer any questions from you guys. Thank you.
Okay, I believe everybody's good. Thank you so much for your talk. It was amazing and very interesting insights about those implementations techniques.
Sure.
And thank you so much for your time. I really appreciate it. And thank you guys for participating in this workshop.
Excuse me, I have a quick question.
Sure.
Yeah, go ahead.
Yeah, so I guess I missed some slides. I want to see how's the implementation with Fibonacci here for the problem we discussed.
I didn't implement the one with Fibonacci because we don't have it from the standard library, and the implementation from scratch will be more complicated than implementing the shortest path itself. So I didn't give it a try.
Oh, okay.
Okay.
Thank you so much, Peiheng. So
Sure.
we are kind of colleague now.
Yes. Yeah.
After my meeting,
here.
I jumped into this workshop. That was amazing.
Okay. Thank you.
Thank you.
Any other question? Okay.
Okay. So if you guys have any questions or have any on the implementation itself, you can go to my GitHub page. And I have all those nodes, all those source code open source, so you can give it a try. And I have the data set there too. So
thank you.
Thank you for inviting me for this workshop. Thank you so much.
Thank you so much.
Have a great weekend.
You too. Bye.